Okay, what is meant by polydentate ligand? Okay, polydentate ligand is going to be a ligand, okay, that is going to be able to form, okay, not only one, okay, it can form more than one, okay, dative bonding, okay, because ability to donate the lone pair, okay, to the metal ion. So how do I actually write it down? Okay, we write it down as in a sense that a species, okay, a species that can donate, okay, that can donate more than one lone pair, okay, more than one lone pair of electron. Okay, that's going to be 1 mark. Okay, to form what? Okay, to form dative. Okay, dative. If you say dative bonding, then it's okay. Or if you want to say coordinate bonding, it's okay. Don't actually use coordinate dative together. No. Okay, so to form dative bonding to a metal ion. Okay, to a metal ion. Okay, to form a complex or whatever you want to actually say, but it's going to be again 2 marks in total. Okay, please take note of this. And then if you look into the structure of EDTA, okay, EDTA is added to a solution containing cadmium, okay, complex. A new complex is formed. So you have this structure of EDTA. The 6 atoms, we need to circle the 6 atoms that will form the bond with the metal ion. Now, the 6 atoms that will form the bond, okay, let me check with Lavi. Lavi, which are the 6 atoms that will actually form the bond with the metal ion?
H2O.
H2O? No. Here they say circle on the structure of EDTA. 6 atoms that will form the bond. So it means the 6 atoms must have the lone pair to be donated. So maybe someone else can try. Maybe Nicole, Trisha, can you try? Nicole, Trisha, are you there?
Yes, sir.
Yeah. Can you try which will be the one that will actually forming the 6 dative bond? Okay. Which are the atoms? For the EDTA, you should know about this. Maybe we'll ask Victoria then. Victoria, which one? I'll look at the chat first. Hold on. Yeah, I thought 2 or more. Okay, because of bidentate. Yes. Okay, yes. Okay, hold on. Yeah, I'll share the screen again. Okay, because the answer should be able to donate more than one lone pair. I think in that sense, Justin, because polydentate, okay, it's not necessarily 2 or more. As long as 1 or more is okay. Even bidentate is considered to be polydentate. So 1 or more should be fine. So even in the answer key, I hope you can still hear me. Okay, Victoria, can you still hear me?
Sir, you were lagging just now.
Okay. To answer, okay, now should be clear. Justin, to answer the question, okay, it should be 1 or more. Even bidentate is considered to be polydentate. Okay, so 1 or more will be the best answer. Even in the marking key, it is mentioned 1 or more. Okay, so no need to say 2 or more. Okay, thinking about bidentate. No, bidentate is also polydentate. So we have monodentate, bidentate, okay, and so on. Okay, but polydentate is considered to be more than 1. Okay, so still okay. So I'll share the screen again. Okay, the 6 atoms that we want to actually form the bonds. Yeah, Victoria, can you actually help us out over here? What are the 6 atoms that will form the bond with the metal ion?
Is it the oxygen?
Yeah. So there are 4 oxygen, okay, and 2 nitrogen, and all of them will actually donate the lone pair. The question is there are total 8 oxygen over here. Which one, okay, will be selected, Charlton? Is it the O negative, or is it going to be the one which has C double bond O?
The negative one.
Okay, very good. Okay, if you look at the textbook, this is very important. Even though in the marking key they say any of the O, okay, but again, when they say any of the O, it means the O that they meant is going to be this O. Okay, 4. And then the nitrogen also has lone pair. Even though this one also have lone pair, because of the structure, they don't follow that way. Okay, so this one, please take note. Okay, not this oxygen. Okay, and then the nitrogen will be this. Okay, they also have lone pair. So total 6. Okay, 6 atoms. Write an expression for the stability constant of equilibrium 1 and state its unit. Okay, so just write, okay, this one divided by these two. This one will not be included because it's water. So here I will write down CDEDTA 2 minus divided by EDTA 4 minus concentration CdH2O6 2 plus concentration. Okay, I wrote it like this. And then they are asking about the stability constants unit. Okay, so when we are looking into the unit that we are going to, we have to work on the unit. So here is going to be mole per dm cube, okay, divided by mole per dm cube to the power of 2. Okay, so to the power of 2, when you cancel left with 1 only. So it's going to be 1 over, okay, 1 over mole per dm cube. So it's supposed to be mole negative 1 dm to the power of 3. Okay, please take note of this. Now, next, you can see that a cadmium ion forms complexes with methyl amine. Okay, they have the stability constants given over there. And I want to write, okay, the new stability constant, okay, the new equilibrium constant, okay, for equilibrium number 4, which is going to be this one. So of course it has to do with these two combo over here. So how to do this? Okay, last time I already mentioned about how to use the KC method, okay, rearranging it properly. So the same thing comes here, okay, where we know the K step 2, okay, you are going to have this one. Let me use it as 1. Okay, this one is 1. Okay, divided by CH3NH2 4 CdH2O6 2 plus. I ignore the water. K step 3. I am going to have maybe this one. I'll replace it as 2. So 2 divided by En to the power of 2 CdH2O 2 plus. Okay, so now I need to actually get the K step for 4, which is going to be, I need to have this one. Okay, so CH3NH2 to the power of 4. And then this one, the number 2. Okay, I can just say 2 divided by, I want En to the power of 2. Then this is going to be 1. So 1. Okay. So how do I actually, from these two equations to get here 1? So you can see 1 over this. Okay, this is 1 is at the below. So what I will do, K step, okay, equals to this one should be 1 over K step 2. Okay, if I do that only, I will get the 1 below. Okay, this one will go up. This one, okay, will go up. Now I need to cancel this one, okay. So I can only cancel when I actually times this with K step 3 directly, because why? This was at the top, this will be at the bottom, they will cancel with each other, okay. And then there is also En2, okay, En2. So I'll just see here, there is En2 as well, okay, En2. So basically I come into this conclusion saying that, okay, in order to get this K step 4, okay, I will come into this concept, which is going to be K step 3 divided by K step 2 is going to be my answer. So this is how I came to that conclusion. Okay, so you need to actually write and analyze. Okay, write and analyze. Okay, I will get that. So the expression, okay, I have that expression, so I'll just leave it over there. So they let me check the answer key. Yeah, that is the even the expression that they want also. Okay, K step 3 divided by K step 2. Calculate the value of Gibbs free energy, okay, for the equilibrium 4 at 298 Kelvin. Now for this one, please remember this formula, Mr. Gopi, okay, I hope you remember, is not so hot, okay, so it means the delta H minus T delta S, T delta S, okay, depends on how you want to memorize, okay, but okay, this you need to know, okay, the formula you need to know. So here, okay, if I actually use this formula, okay, I want to calculate Gibbs free energy for equilibrium 4. Okay, so delta H, okay, is going to be given. Okay, you can see here. So what I want to use, okay, so better use straight away one of the units. So let's say if I want to use kilojoule, okay, you see both of them are different units. So if I want to use kilojoule, so 0.840 minus T, T is going to be, must be in Kelvin, so 298, okay. And then the S, okay, they already give the entropy, okay. The entropy is going to be in joule, so you need to divide by 1000, so 0.0809 kilojoule per Kelvin per mole. So times with this and calculate for me what is going to be Gibbs free energy. Okay, I will take the answer from the marking key over here, but do always check. You need to actually always double check, because later I'll show you one of the significant figure that is given in the marking key is wrong. Yeah, so please double check. Okay, so this one you will get negative 23.3 kilojoule per mole, because they even want you in kilojoule per mole. And this is telling us that, okay, Charlton, okay, Gibbs free energy negative. Is it spontaneous at 298 or non-spontaneous at 298?
Spontaneous.
Very good. Okay, so Gibbs free energy must be negative in order to be spontaneous. Okay, so please take note of this. Okay, if you have entropy is positive, then it's possible. But again, that is the reason why I ask you to watch my video. Okay, because here they are asking you how the value of Gibbs free energy will change as the temperature increases, and explain your answer. Okay, this is what I wanted you to actually see from the video. Okay, if you have, okay, S negative, okay, entropy is positive, H positive, H negative, okay, the one that is going to be easier to identify is when the quadrants are having different positive and negative. Like for example, okay, if I see this one positive and negative, this quadrant are different. And if you look at this quadrant, negative and S is positive is different. So we can actually identify them easily. How? Okay, because if you have entropy is positive, okay, more entropy, and then delta H is negative, is exothermic, is of course is going to be always spontaneous. doesn't matter any temperature, it's going to be spontaneous. Now if you have, okay, entropy is negative, okay, and then the delta H is positive, okay, endothermic, the reaction is going to be non-spontaneous, doesn't matter, okay, doesn't matter whether any temperature that you use, okay, it's quite easy to determine, okay, but okay, all this we determine using this formula, okay. Now in order to determine for these two quadrants, okay, this one I have explained to you, okay, in the video, okay, if let's say solid to change into liquid, okay, I give you this example, ice and water, ice and water, let's say at the equilibrium it's going to be 25 degrees Celsius, okay. So from what condition ice can actually change into water, okay, they can change into water because entropy increases, and it can be only happening because it will be endothermic, they need to absorb energy, then the forward reaction is going to be favored. In order to do this, okay, you need to have higher temperature than what? 25 degrees, must be more, okay. So you want to change ice to become water or something, you can predict using that. So what I will do, okay, positive and positive, temperature is high, you can see here, positive and positive, this quadrant, it will be only spontaneous when temperature is higher, okay. And the next one, if you want to identify, you see ice, water. In order to change water to become ice, what you are trying to do, you are going to decrease the disorder, okay, minus, okay, which is going to be entropy is negative. And then what we need to do, okay, is going to be exothermic reaction, okay, water to become ice, they release energy, okay. So this thing can only happen, okay, if you have lower temperature, okay. So just use this one, negative, negative, temperature is low, so negative, negative, okay. So this quadrant is, this reaction is only spontaneous when the temperature is low, okay. And all this knowledge is important. Why? To answer this kind of question, they say that state how, okay, the Gibbs free energy changes when the temperature increases. So when we look at here, both of them are positive, it means that they are going to come into this quadrant, positive and positive. So this reaction is only spontaneous when the temperature is going to increase. You see, temperature is increasing, it's going to become spontaneous. So therefore, I know that when temperature increases, my Gibbs free energy will become negative. So they ask you to explain your answer. So how do you explain your answer? They say you need to say when temperature is increasing, your Gibbs free energy is going to become more negative. Okay, your Gibbs free energy is going to become more negative, and then they ask you to explain more. I think this one you need to actually use the formula if you want to explain more. Okay, why? Because if this is positive and if this is positive, okay, when temperature is going up, how this one becomes more negative? Okay, why? Basically this is positive, so of course if it is going up, this entire value is going to become bigger. Okay, so you can say when the temperature increases, this value increases, okay, making, okay, Gibbs free energy become less negative. Okay, sorry, it is going to make Gibbs free energy become more negative. Okay, so it will make it more spontaneous. Will they award marks for the spontaneous? No, because basically you see, they don't actually even require you to mention about whether the reaction is spontaneous or not. Okay, so you will get the marks not for the spontaneous, you will get the marks for these two. So it is understandable if students are getting lower mark, but again, okay, do remember this is going to be only 1 mark. If they give you 2 marks, then possibly some students might lose mark because didn't mention about this. But okay, as long you can mention that your Gibbs free energy is getting negative because of something, okay, because whatever explanation, you should be able to get 1 mark. Okay, please remember that. Okay, but you need to explain. Okay, so that explanation part, okay, refer to this, not the spontaneous part. Okay, The next question, okay, anyway, it's already 10 o'clock, okay. Let me actually just go through. Can we just finish this? Okay. Give me 5 minutes here. Okay. Now, describe and explain how solubility of sulfate varies down the group. Okay. Solubility of sulfate, okay, they will decrease down the group. I will repeat this again tomorrow. Okay. They will decrease down the group. Please remember this one. Okay. Your previous paper. Okay. In the same year. Okay. We have actually have this SHL. Okay. What does it mean? Okay. This one sulfate. This one is going to be hydration. This one is lattice. So I told you sulfate hydration decrease more than lattice. Okay, if you want to remember for hydroxide, lattice decrease more than hydration. So I told you to remember SHL. So here, okay, explain. So it's the same explanation. Okay, your hydration decreases more than lattice energy. Why? Okay, because SO4 is going to be bigger. Okay, but no need to explain about that. I think this one is already good enough. Okay, you mentioned about, okay, it decreases. You mentioned about this, and you just mentioned about your enthalpy of solution. Okay, become less negative. Okay, when it becomes less negative, basically the solubility is going to become less soluble. Okay, so it means if the solution is positive, generally it's going to be less soluble. Okay, in order to be soluble, the enthalpy of solution must be negative. Okay, so please refer to the marking key, all this. And then the trend of the decomposition of temperature is similar to group 2 carbonates. For carbonates and nitrates, do remember as you go down the group, it's going to be difficult to decompose them. Okay, so carbonates becomes more stable down the group. So it's the same as the group 2 peroxide. They try to relate to that. So they say that suggest which one will decompose at lower temperature. So you see this one, barium is bigger, calcium is smaller. Smaller ionic radii. Okay, so they have higher charge density. So calcium ion will be able to have a better polarizing power. So they will actually polarize the peroxide more, and the bonding between the oxygen and oxygen in peroxide, they are going to actually break easily. So that's the reason why, okay, calcium peroxide will decompose at lower temperature. Okay, so that's going to be 2 marks. Okay, see what are the areas that they want to actually give you mark. Okay, and then writing the equation, no problem, just follow, okay, what they have given you. Okay, just follow. This one, okay, for this one as well, if you want to write the KSP and so on, okay, just write like normal. Okay, but I think the common confusion that students will have is this one, the concentrated of saturated solution. How do we know? How do we know? And so on. I think the best way to look at it is by looking at this. If you have calcium, the same compound in solid, okay, if they change into aqueous, okay, the concentration of this aqueous alone, okay, this aqueous alone is going to be this, okay, 5.6 times 10 negative 3. So this one, they can actually change into calcium 2 plus and 2iO3 2 minus over there. So do remember, if I have like this, aqueous changing into that, if this is 5.6 times 10 negative 3, this one will be 5.6 times 10 negative 3 also, aqueous. But this one is going to be 2 times 5.6 times 10 negative 3. Please remember how to do this, okay? So that's the reason why, okay, this one is 5.6 and this one must times by 2. Okay, so the expression quite easy, unit quite easy, okay? The KSP value, okay, calculate, okay, use replace with the value that we have, you will get this. This is what I want to highlight. Check your marking key because the marking key states 7.03. Okay, it is impossible to get 7.03. Okay, that's why double check with your marking key. It's supposed to be 7.02. Okay, times 10 negative 7. Okay, and then the last one that I want to actually mention over here. Okay, when you add a few drops of concentrated calcium nitrate, white precipitate form. Okay, you see when you have calcium nitrate, they're soluble, And then the only way it will react in this case is by forming this precipitate. Okay, so there's no other precipitate that will be formed. So identify correctly. This is going to be my precipitate. Why it cannot be calcium nitrate? Calcium nitrate, all nitrates are soluble. Okay, please remember that. And then what happens over here? Give explanation. Okay, the explanation is quite simple. Okay, when you have this equation, when you are adding calcium nitrate, you are adding calcium ions. Okay, according to LCP, okay, when you increase the concentration of calcium ions, okay, calcium ions must be removed. So the position of the equilibrium is shifted to the left. So when you shift the position of the equilibrium to the left, solubility decreases. Okay, solubility decreases. So that's the reason why the solubility decreases. Okay, and what is this effect? This effect is known as common ion effect. Okay, so the solubility decreases because there is a common ion effect. Okay, that makes the position of the equilibrium shift to the left. Is there any marks for position being shifted to the left? No. Okay, here they just want you to identify and give explanation. Okay, the explanation is, yeah, position of the equilibrium is shifted to the left, but why is that? Okay, because of the common ion effect, and it will decrease the solubility. Okay, if let's say they give you 3 marks and then you mention about the position is shifted to the left, yeah, they do accept that point. Okay, but for 2 marks, no, they are not going to accept. Okay, it's already 10:07. Okay, that's it. What I want to discuss for today. Okay, please continue. Okay, with the rest of it. Okay, any questions before I end? It's already 10:07. Lavi, any question? Okay, so this part, okay, we are looking into the calculation aspect of chemistry. So please be very, very careful when you are dealing with these kind of questions. Read the question properly. Okay, so they say iodized salt. Okay, so this one they say is a mixture. So it's a mixture of sodium chloride and NaIO3. Okay, so it is made up to 250 cm cube. Okay, volumetric flask. Okay, and then from there you take 50 from there, and then you are going to actually react with excess of iodide, acidified potassium iodide, and you are going to actually get I2 and so on. So they say that the iodine produced, okay, it requires this amount of aqueous sodium thiosulfate, which is going to be this one. So you need to actually do a lot of steps over here. So they have requiring this, and then what you need to do, you need to work backwards. So here, what I need to do is, okay, this I can calculate what is going to be the number of moles of thiosulfate ions. So I calculate the number of moles of thiosulfate over here, 12.5, okay, times 0.02, okay, and then divide by 1000. I'm getting this number of moles. Okay, this number of moles, okay, do take note, 2 moles, and I want for 1 mole, so I need to make it half. So you can see number of moles of I2, I make it into half, so divide by 2, I'll get this. So this 1.24 times 10 to the power of -5 is the same thing that I have over here. Okay, you don't need to times by 3. Please remember this. Okay, that is the number of moles that is actually going to be produced over here, which is exactly 1.24 times 10 -5. Okay, so if you know that, okay, what we can actually find out, because this is going to be excess. Okay, I can find out what is going to be my number of moles of IO3 minus. Okay, so 3 and 1. So you divide by 3. So divide by 3. And I am going to get this number of moles. And please take note, this part, I took 50 cm cube. Okay, so when I took 50 cm cube of this solution, okay, so it means that this is going to be the number of moles of this in 50 cm cube. So let's actually look into, like, for example, if you look over here, if I take if let's say you prepare this much, okay, and you only took this much 50 cm cube, okay, so you need to still consider the entire thing, okay, the number of moles. So what you need to do, you need to convert it to 250. Okay, so you need to times by 5, okay, to get 250. So here you times everything by 5. Okay, when I times that, I'm going to get this number of moles. Okay, once I have this number of moles, okay, please actually really understand the concept, because okay, we know that okay, it's a mixture. Okay, there is sodium chloride and NaIO3 over there, and you calculated the number of moles of the ion. So you need to still relate that number of moles of that ion to the one that you are going to calculate. I think this is what students tend to forget. Okay, sometimes they make mistakes. Okay, because it's not 1 mole to 1 mole. Okay, so the thing is, in this case, it happened to be 1 mole to 1 mole. You can see that if this is 2.07, one NaIO3 will give you Na plus and IO3 minus. If this is 1 mole, this is 1 mole, this is 1 mole. So it's the same. It happened to be, but not all the time it's going to be like that. Okay, please take note. Okay, so I found out that my number of moles of this is going to be that, and I can calculate my mass. Okay, so use the number of moles equals to mass over mr. Okay, so you can calculate the mass, number of moles times the mr. So number of moles, okay, times the mr of what? Okay, because you are not actually going to take this one doesn't actually make sense if you calculate the mr. That's why you need to calculate for this one. Okay, so NaIO3. Okay, so 23. Okay, look at your periodic table, then you can get this. Okay, and you will get this amount of gram. Okay, in gram. So it means that out of 50 gram, okay, out of 50 gram, you have a very small amount, okay, which belongs to an AiO3. And they can actually continue to ask what is going to be the percentage, okay, of NaIO3 in this sample, percentage by mass. You can also need to do, which is going to be, if they ask you percentage by mass, then you just put 4.09 times 10 negative 3 divided by 50 times 100%. Okay, that is actually if they ask percentage by mass. Okay, but here they don't want. Okay, I think they already feel that this question is a bit confusing for, I think in many levels, some of the weak students cannot do. So they just happy with that. They just stop at 3 marks. Okay, so if you do this, okay, you will actually get this answer. Okay, 3 marks, and they stop over there. But okay, some questions they can continue to percentage by mass. Okay, so please take note of that. Okay, and then here, okay, the next one is the half equation for the reduction is given. Okay, so they give you the half equation. Use the data from the data booklet, okay, to predict whether the reaction is feasible when you use aqueous solutions of acidified iodate, okay, ions. So when I use this, okay, so when I mix that with bromide ion, okay, I need to say see whether the reaction is going to be feasible or not. Okay, so here when I see the whether the reaction is feasible or not, okay, I will actually need to look for the bromide ion. So bromide, okay, if you look at the data booklet, you have this bromide ion, bromine over there. So if you have this, okay, the E value is 1.07. This is taken directly from the data booklet. And then you have also 1.19 over here. Okay, so we want to actually identify whether it's feasible or not. First, compare. Okay, make sure both of them are in reduction form. 1.19, 1.07. Okay, the one that has more positive, they will move to the right. So they will stay as it is. But this one's supposed to move to the left. So automatically, this is going to become negative 1.07. So if you want to find the E total, okay, the E total or the E cell is going to be 1.19 plus negative 1.07. If you do that, you are going to get positive 0.12. If you have positive 0.1 more than 0, which is a positive value, this is going to be an indication that the reaction is feasible. Okay, so explain your answer. Okay, just tell, okay, the reaction is feasible because the E value is going to be positive 0.12 volt. Okay, that is enough already. Okay, but you cannot just say feasible, okay, and then the reaction can happen, or without actually giving information over here. So in order to get the marks, that even though it's 1 mark, you need to mention about the E cell, okay, 0.12. Do I need to show how did I get it? No need. I think even if you can actually show some kind of working here, here is okay, still fine. Okay, so no need to actually do show a lot of working over here. Basically, you just say the reaction is feasible because it's going to give you a positive E value, which is going to be 0.12. It's okay, it's fine. Okay, so that is actually what you need to do over there. Now, the next is going to be iodate ions. Okay, they react with sulfide ion in acidic condition, acidic solution at pH 5 as shown. So they actually give you this, and then they have given you some data over here. I think they are very generous in this paper. I think very easy. They are not actually asking you to identify the order of the reaction. They are giving you all the data. They tell, okay, first order to what? First order to this, first order to that. Okay, but do remember they can actually give you a table and all the data related to initial rate of reaction and ask you to analyze. I think you know how to get it also. Okay, but again, in this case, they are just straight away asking you to write the rate equation. Write the rate equation. Make sure you put the K. All these are first order, so everything is going to be first order. Okay, I put over there. And then they are asking for the unit of the K. So if you want to find the unit of the K, you need to know the rate. This is going to be the formula. Okay, concentration divided by time. Okay, so that is going to be the rate. If I want to find what is K, K is going to be rate divided by concentration. There are three concentration. Okay, so it is divided by to the power of 3. Okay, so if I cancel that, okay, this entire thing I cancel, okay, I'm going to get 2 over there. So I'm going to get still per second, okay, to the power of 2, mole negative 2, and then dm, okay, when I times, is going to be dm to the power of 6. Okay, that is going to be the unit, and make sure, okay, you can actually do this. Yeah, it is very important. Okay, and then here, this is also super easy actually. Okay, no need to get confused with this kind of question. They say that the rate of reaction depends on the pH of the solution. Okay, assume all the other concentration remains the same. It means nothing is changed. Okay, so they are asking to use the expression x, okay, divided by rate at here, divided by this rate to calculate the value of x. Now, do remember, okay, the rate equation, okay, the rate equation, they are telling all the other values are the same. It means the k, okay, the k is going to be, if I write down the equation, is going to be x equals to k, concentration of IO3, okay, I just write down H plus. All this happen at pH 5 divided by K, and this one happens at pH 4. Okay, what I can see over here is you can cancel because this one is the same. You can cancel this concentration. They say all the other concentration are the same, so cancel over here. The only thing that will stay is the concentration of H plus. So you can calculate the concentration of H plus. Okay, because pH is 5. You can calculate negative log H plus equals to 5. What is H plus? Okay, 10 to the power of negative 5. Okay, and then pH 4, negative log H plus is 4. So this is going to be the thing. So if I want to find the X, okay, just put the concentration of pH 5. pH 5 is this one, 10 negative 5, divide by 10 negative 4. Okay, and you are going to get 10 negative 5 plus 4. Okay, and then you are going to get 10 negative 1, which is 1 over 10, which is 0.1. Okay, if you want to put 0.1 is okay, but in the marking key they put 0.10, up to you. Okay, normally they put in 2 decimal places. If you want 3 significant figures, I think if you put like this, then it will be too weird. Okay, so it's either 0.10 or 0.1 should be okay, as long as you show the working. Anyway, it's only 1 mark. Okay, don't overthink it. Yeah, so the next part, okay, is going to be the completing the electronic configuration, okay, for of an isolated gaseous nickel ion. Okay, so here if you look at your periodic table, okay, I will notice that the way to use is going to be argon 4s2. This is nickel, yeah. So nickel I will see is 4s2 3d8. Okay, position number 8. So I have all this data. So once I have that, I know, okay, I put argon. Okay, I will fill in 4s2. So fill in 4s2 3d8. I put like this. Now, the moment you want to remove the electron, okay, please remember you are removing the electron from 4s also. Okay, when you add from 4s. When you remove, you also remove from 4s. I think this one is one of the common mistake, okay, that students will do. So you remove the 2 electrons from here first before moving to somewhere else, because you only need to remove 2. Okay, you remove 2, so this one will be empty. The rest you draw. It's the same thing. I just put over here, and that will give you the 1 mark. Okay. So please be very, please make sure that you don't make any mistake over here. Now, of 4 marks, this is actually unusual. Okay, but not surprising. Okay, unusual but not surprising. They are asking you to explain the origin of color in transition element complex. Okay, I hope you remember. Okay, even though in the marking key here they didn't use certain terms. Okay, I think you need to use the terms. Okay, in the marking key they say that the d orbitals, they split into 2 energy levels. Okay, that is what they mention in the marking key. But I don't want you to just simply say that. Okay, you can say d orbital split into 2 energy levels is okay. But I think the better one will be d orbitals will split into 2 sets of non-degenerate orbitals. Non-degenerate means different energy. Okay, so d orbitals split into 2 sets of non-degenerate orbitals. That is going to be 1 mark. Okay, the next one, okay, you when light, okay, when there is a light, okay, it will give, okay, energy. Light comes with energy. So that energy from the light, visible light, okay, will be absorbed by the electron. From where? The lower non-degenerate orbitals. Okay, the lower non-degenerate orbitals, the electron, okay, will be excited or will be promoted to higher d orbitals or higher energy level. Okay, so that's going to be 1 more mark. Okay, how? Okay, they are going to absorb the energy from the frequency of visible light. So just now I already mentioned about this. 1 more mark. And once it is absorbed, the color that you see, the observed color, is complementary to the light of absorbed. So it means whatever thing, whatever energy that is absorbed, okay, what we see is complementary to that. Okay, so the term complementary, okay, is important. Okay, so that is going to be another 1 more mark. So here, okay, you don't have any choice. Okay, you need to mention about all these 4 points. It can be more. Okay, it can be more. Okay, but these 2 energy levels, I would like you to use 2 sets of non-degenerate orbitals. Okay, electron promoted to higher d orbitals. Do remember, promote only is not enough. You need to mention higher d orbitals. Okay, by what? Absorbing the energy, okay, from the frequency of light. Okay, and then observed color is complementary. So all these will give you the 4 marks. Okay, so the next one, okay, is going to be, so Gabriela Nicole is asking, so non-degenerate orbitals is high and low energy level. Yes, correct. Okay, so we have, if they say degenerate orbitals, they have same energy level. So when they say non-degenerate orbitals, means they have different energy level. Okay, so 2 non-degenerate orbitals. Okay, and then the lower electron, they can actually go to the higher non-degenerate orbitals. Okay, and then because of they are absorbing the energy. Okay, so whatever the color, okay, the frequency of visible light that it has been absorbed, okay, when we see, okay, it's going, we are only going to see the color that is complementary to the light that was absorbed earlier. Okay, so this is very important. Now I do notice one thing, okay, with the recent paper. So let's actually learn, yeah, continuously learn. Okay, If you notice the recent papers, especially when it comes to transition elements, when I taught you the topics, I told you to memorize this, memorize that, this color, that color, I told you about that. Okay, but if you look at the trend of the question, okay, this one based on observation only, but it's not actually nothing conclusive. Okay, this is based on what I observed. I think they are moving away from testing you to directly on memorizing on the color of the complex ion. Okay, so this one is actually maybe a good news for certain people. Okay, because if you don't memorize, it's okay. They just want to test your knowledge. But for very good students, okay, I know that you want to get the mark, utilize every opportunity that you have. Okay, then you want to memorize, please memorize. You want to memorize with the equations, please memorize. Okay, whatever it is. Okay, a lesson on that has been shared to you, okay, through another video. Please go and see that. Okay, so about cobalt, okay, about nickel and so on. Okay, please actually go and see that video. Okay, but here they are telling that hexa aqua nickel ions, okay, they are telling the colors itself, they are green, so they already say they are green, and then they are going to form green precipitate with hydroxide ion, okay, in equilibrium 1, and a blue complex ammonia, blue complex with ammonia in equilibrium 2. So this is green, blue and green. Okay, so this is going to be hexa aqua nickel. Okay, so this one, both of them are green. Okay, they didn't write down, but it's a green solution. Okay, not precipitate solution. Okay, but this one is green precipitate and it's a blue complex. I think it's still solution. Okay, so okay. Now use the LCP, okay, principle to suggest explanations for the following observation. We need to explain why when we add aqueous ammonia, okay, drop-wise, okay, to this hexa aqua nickel ion, a green precipitate is formed. So please look at which equation that we want to use. Okay, we want to use equilibrium number 1. So if we are using equilibrium number 1, I want to say why when I add dropwise, a green precipitate is formed. Okay, why I am not using equilibrium 2, there is a reason. Okay, so when they say aqueous ammonia, okay, aqueous ammonia, it means that, okay, in that water, in that ammonia with water, there is going to be a presence of water. Okay, there's a presence of water. Okay, or the presence of basically ammonia with water. Okay, ammonia with water, they are going to give you NH4 plus and OH minus. Okay, please remember this. Okay, they are going to have ammonium ion and also hydroxide ion. It means that, okay, when I have, even though I'm adding ammonia, I am not going to use equilibrium 2 because it's aqueous, because the OH minus is being formed, okay, with when you have ammonia. So you are going to get ammonium and hydroxide. Now this hydroxide, okay, when you actually have more, okay, what happens is going to be when you have used LCP, okay, when the OH is more, the position of the equilibrium will be shifted to remove the excess hydroxide ion. So in when that thing is happening, okay, you are going to get, okay, when the forward reaction is happening, you are going to get a green precipitate. So that's why they say the green precipitate is formed. So we need to explain why. Okay, so you need to explain when ammonia aqueous, when aqueous ammonia is added dropwise, okay, the ammonia will react with water. Okay, the ammonia will react with water to give you ammonium ion. Okay, to give you ammonium ion plus hydroxide ion. Okay, so this is going to increase the concentration of hydroxide ion. Okay, when that is happening, okay, according to LCP, okay, you need to remove the hydroxide ion. Okay, so how do we remove the hydroxide ion? by shifting the position of equilibrium 1, okay, shifting the position of equilibrium 1, okay, to go to the, okay, so we need to actually decrease. So how do we decrease it? By moving it to the right, okay, so it means the forward reaction is going to be favored. Okay, in that sense, okay, you are going to get green precipitate of, okay, green precipitate of NiOH2. Okay, this is actually mentioned over there. 1 mark. Okay, so should quite easy. Yeah. Now this is the second part is a bit tricky. Okay, the second part is a bit tricky. They say explain why a large excess of ammonia, when you put ammonia dropwise, okay, now you get green precipitate. But now if I suddenly put a lot of aqueous ammonia, okay, a lot of aqueous ammonia, are we still going to focus on OH minus? The answer is no. When you are using a lot, excess ammonia, it means the concentration of ammonia is going to be increased. Okay, so when this concentration of ammonia is increased, the position of the equilibrium will be shifted to the right. Okay, so when it is shifted to the right, okay, you are going to form more of this. So this one, do remember blue solution, more of this. So the next question, the part that I say tricky, you don't actually end over there because you still need to explain why the green precipitate dissolves. Okay, so how to actually explain that? Okay, the green precipitate dissolve because, okay, when in equilibrium 2, okay, when I actually react, okay, the position was forward position. The direction is going to be forward direction. But okay, when I actually react, okay, when I react with the aqueous ammonia, okay, when this is going to increase NiNH3 6, okay, when that is increased, okay, my equilibrium 1 will change. Okay, so how my equilibrium 1 is going to change? Because, okay, because I am going to actually change the concentration of this one. Okay, hold on, yeah, let me connect to my Apple Pencil. Okay, let me actually continue again. It's a bit tricky part, yeah. So the tricky part is, okay, they are asking, okay, when you put a large excess of ammonia, okay, so a lot, so it will move to the right. You are forming a lot of this. Okay, when you form a lot of this, you are going to actually make, okay, this one be more. Okay, you can see Ni, okay, NiNH3 6, which is going to be more. Okay, in this case you can see the Ni, okay, H2O6, okay, sorry, NiH2O6 is going to become less. Okay, the concentration will become less. When that concentration becomes less, so when this is going to be less, you are going to actually make the equilibrium 1 to form more towards this side. Okay, to form more towards this side, to increase the concentration of the NiH2O6. So in that sense, what happens is this green precipitate is going to dissolve. That is going to explain the green precipitate dissolve, and a blue solution is going to be formed. A blue solution means, okay, here is actually they mentioned is going to be blue, yeah. Okay, this one is blue. Okay, blue solution. NiH2O6, okay, they are going to be green. So basically they are, you explain about green over here, equilibrium 1. When you say blue solution, you are explaining using equilibrium 2. Okay, so how do we actually present our idea over here? Explain. Okay, when aqueous ammonia is added dropwise, okay, so ammonia will react with water to give you ammonium and hydroxide ion. Okay, So when that happens, okay, the concentration of hydroxide ion will increase. Okay, so because of that, the position of the equilibrium number one will be shifted to the right. Okay, so that is going to be what's going to happen. And then for the here is going to be when a large excess, okay, is added. So first what happens, okay, is going to be ammonia. So for second equilibrium number two, they move to the right. Okay, in that sense, okay, what happens, you are going to actually NiH2O6 2 plus, they will decrease the concentration. When that it decreases, okay, you need to actually follow equilibrium one. Okay, you need to actually make sure that NiH2O6 is going to be reformed again. So the position of the equilibrium in equilibrium one is going to be moving to the left. Okay, when that is going to happen, moving to the left, okay, what happens is going to be the green precipitate. Okay, it's going to be green PPT. Okay, it's going to be dissolved. Okay, is going to be dissolved, and at the same time, okay, you can actually mention that the blue solution is going to be formed, which is going to be under equilibrium 2. Okay, blue solution form. And then here, okay, the complex ion, this is also very, very easy, okay, compared to the previous questions that we have done on this, okay. They have given the ligands and so on. You can see the ligand is Br, Br, Cn, and Cn, okay. So we need to identify, name the type of isomerism. So you can say either geometric or cis and trans, okay. So you can actually choose which one you want to select. But again, you need to actually put them properly. Like for example, BR. Okay, if you put BR at the same side by side, then it's going to be cis. If you put BR across, then it's going to be trans. Okay, so 2 marks only. Okay. Next, okay, is going to be number 4. Okay, when benzene undergoes nitration, a nitro group substitute at carbon atom. So benzene, okay, so when they undergo nitration, so you are going to get this. So please remember nitration, okay, what is going to be the conditions required? Okay, it must be HNO3, okay, with a concentrated nitric acid, concentrated sulfuric acid, okay. Is it sulfuric acid or hydrochloric acid? Okay, you can check on this. Okay, you are going to have concentrated acids. Okay, and after that you need to have 55 degrees Celsius. Okay, and then you heat under reflux. Okay, so when you do that, okay, you are going to actually get, okay, this, okay, NO2 then. So here, okay, do we need any halogen carriers? Okay, let me ask you, maybe Victoria, do you need any halogen carriers for here?
No, yeah.
Okay, this one, all this, okay, please actually go and find out. Okay, in this case I don't think so you need any halogen carriers, because the reaction, okay, the acid, the this one NO2 minus, they are very reactive. Okay, when they are very reactive, I don't think so need to have any halogen carriers. Okay, but please check again. Okay, so here we want to actually identify the shape, okay, the geometry, okay, around the substituted carbon atom. If it is in benzene, so let's actually see in benzene, okay, what is going to be the shape. So in benzene, there's one H and then 3 bonds only. Okay, one of it is the delocalized electron. So if I have 3 bonds only, there is no lone pair. So of course, my shape is going to be trigonal planar. Okay, very easy. And then they say the intermediate complex. Now the intermediate complex is going to be, you are going to have one hydrogen here and then NO2 here, and then here they will have this something like this. Okay, this is going to be the intermediate compound, and you can see that each carbon here are bonded to 4. Okay, if it is bonded to 4, then they have to have this tetrahedral arrangement. Okay, and then the last one in the nitrobenzene product. So in this nitrobenzene product, you have 1, 2, and then another 1. Okay, so 3. So this is going to be again a trigonal planar. Okay, 2 marks. Now, next, naphthalene is going to be an arene hydrocarbon. Okay, do remember what is the difference between arene and alkyl? What is the difference between arenes and aliphatic? Okay, aliphatic is more towards straight chains. Okay, they don't have any benzene inside. Okay, that is going to be aliphatic. But in this case, they already mentioned, okay, you have all these arene hydrocarbon. When naphthalene, okay, when this molecule undergoes nitration, a mixture of two organic compounds is formed. Okay, each of the compound forms contain one nitro group. So you cannot have more than one. So it means if I have one nitro, if I decide, okay, to have the NO2 here, okay, it's okay. Okay, that's it. Okay, but okay, if you they have mentioned a mixture of two organic compound. Okay, if you have two organic compound, then the position. So if I put NO2 over there, okay, if I put the NO2 over here, they are different. Okay, if I put the NO2 over here, can or not? Okay, can, but they are the same as this. Okay, they are same as this. If I put the NO2 here, can or not? Can, but they are still the same as this. Okay, so there are only maximum 3. Okay, the next is going to be naphthalene can be oxidized under certain conditions, okay, to carbon dioxide and water. Now construct an equation and then they ask you to use the O. Yeah, yeah, Anita. Why the structure in 2 is different? Which 2? Oh, why this structure is different than this? Yes. Okay, you see here, if I actually put, okay, in this way, if I have, okay, a structure naphthalene, and then if I put the NO2 here, okay, this is going to be a different, the carbon environment. You see the carbon environment is attached to the carbon that is in another benzene, and this carbon environment is going to be with the H. If I actually put here, okay, my carbon environment is going to be different. Why? I am going to attach to C, that is going to be attached to one more H, and I am going to actually put it to C, that is going to be attached to one more acid. So it means one more environment, the H. So this is going to be a different environment compared to this environment. But if I go and put, okay, like for example, if I have like this, and I go and put NO2 here, the answer is still the same as this. If I go and put the NO2 here or NO2 over there, still the answer is still the same. Okay, so the only thing that is going to be different, if rather than putting it over here, okay, you can actually put it further. So this is going to be another different environment. Okay, put the NO2 to different place, okay, and you will get a different environment. Now, naphthalene can be oxidized. So this one also very easy to get. No need to actually worry so much. Okay. Here, if you have this C10H8, they already mentioned. They say it can be oxidized. Just put the bracket O. And then they say they give you the product. They have the product. What you need to do is you don't need to worry about the mechanism. How come then suddenly this one break and then get this? No need to worry. Just look at the data. This is going to be 10. So must be carbon in form of carbon dioxide. I need 2 carbon. So I put 2 there. Okay, carbon dioxide, I put 2. And then I also noticed the hydrogen supposed to be 8. So the when you look at here, okay, I have 4 hydrogen. So I need another 4. Okay, so I just put over there. So the other oxygen on my right hand side is actually like extra. Okay, so how do I actually count the extra? 2 plus 4, okay, plus 3. I am going to get, okay, 9. Okay, so I'm losing 9 oxygen. Okay, when I lose 9 oxygen, okay, I need to actually put the 9 over there. But when you are losing the 9 oxygen, okay, sorry, yeah, when you are actually losing the gaining the 9 oxygen, okay, you are going to get total 9. So please actually make sure everything is properly balanced, okay. So you can double check, okay. When you double check and everything is okay, then it's good to go. Okay, it's good to go. And the last one, okay, that I want to discuss for today is going to be naming the type of reaction, okay. So the indicator, you have this phenol, okay, this, and giving you the phenolphthalein. Okay, so here what I notice is, I notice like when I have phenol, okay, this is phenol. This is going to be connected directly, okay. When it is connected directly, it's supposed to be something like electrophilic electrophilic substitution, okay. Electrophilic substitution supposed to be happening, okay, because it's actually directly involving the ring, okay. So in this case, okay, in this case we do when I have this, okay, I do not write down it's going to be electrophilic substitution because they have mentioned type of reaction. They didn't say mechanism of the reaction. So the type of reaction, you need to analyze what actually happening. Okay, so basically the double bond O, they are going to go out, okay, and then they are going to be substituted with one of the H. They remove the H. So you have one H coming from each side, okay, one H remove, one H remove, and this, once you do that, okay, the another O from here was removed. So they are getting H2O. So the best answer, okay, is going to be either you mention it's a condensation reaction, okay, condensation, or there is another term that you can actually use, which is going to be addition elimination reaction. Okay, addition elimination reaction. But I think condensation will do because you can see H2O is given up. Okay, so the rest I want you to continue. Okay, you have 15 minutes. Okay, you can continue. But before I end, any questions? This will join later. So number 6, the class of polymers called polycarbonates are made by the reaction of carbonyl dichloride with a diol. Okay, so you are going to get a polycarbonate and you are going to get HCl. Okay, so when I look at this, I see there is going to be 2 OH groups. Okay, so I have R, another OH. So if I have C double bond OCl, Cl, okay, I can see that maybe this one, okay, they will come out, and then this one with another diol, and this one, okay, with another this molecule. So they are going to give you this polycarbonate. So we are removing certain things. Therefore, the type of polymerization here is going to be condensation polymerization. In our syllabus, we have 2 types of polymerization: addition polymerization and condensation polymerization. So addition polymerization we see when we have unsaturated hydrocarbon. So whenever they have double bonds, okay, then we can actually have addition polymerization. In this case, it's a condensation polymerization. So Nalgene is a polycarbonate formed from diol P and COCl2. So something similar. Okay, so if I have C double bond OCl, Cl, okay, and what will happen? Okay, let's say I just put another one molecule over here. So similar reaction will happen. Okay, the H will go out with the Cl, and this H will go out with this Cl. So what we are going to have, okay, similar, this one will also go out, this one will also go out, but they want one repeating unit, not the entire polymer. So how do I draw? Okay, so this one I'll just redraw again. So CH3, CH3, O. Now this O will be connected to C, double bond O, then this is going to be, there is one part. Okay, so here at this side, they supposed to have O connected also with C double bond O, then another part. But okay, when you want to draw one repeat unit, okay, better to look at this structure here. This is one repeat unit. You see carbon double bond O, okay, and another O. So this was something like similar to that, and it ended from R with O, so ended over here. So to show one repeat unit, you do not need to show this part. Okay, you do not need to show this part, so I'll just put, you just need to show up to here, up to here. So if I want to, better way is to remove this. This is going to be one repeat unit. Okay, one repeat unit. Now, Nalgene is a strong and tough polymer. Identify two types of intermolecular forces that are responsible for these properties of Nalgene. So intermolecular forces, you see we have hydrogen bonding, we have van der Waals forces of attraction, we have permanent dipole-dipole bonding. Okay, there are three. So if you look over here, the one that I need to include here, I can see straight away, okay, there is no hydrogen bonding. Why? Hydrogen bonding must have a hydrogen bonding with NOF. Okay, so I don't see that. Okay, there's only oxygen here. So here, I will ignore this part. So I will have van der Waals forces of attraction. Okay, so just put van der Waals forces, and we can also have, okay, the permanent dipole-dipole forces of attraction. So van der Waals forces, in your marking key, they give it ID forces, induced dipole, or London forces. Okay, but all these are van der Waals forces of attraction. Okay, so this one is going to be, you can actually write down van der Waals forces, no problem. And here is going to be permanent dipole forces. But again, if you want to be safe, okay, so instead of writing van der Waals forces, you still want to actually be safe, then induced dipole, induced ID forces, ID. It's supposed to be temporary dipole, induced dipole. Okay, but it's okay, we'll just follow ID forces. Okay, you can still give it as van der Waals forces. Okay, still okay. Now, proteins are polymers of amino acids, and complete the table to show how the secondary and tertiary structures of proteins are stabilized. So secondary structure, okay, you need to know secondary structure is stabilized by hydrogen bonding. The groups that are involved, okay, is going to be the carbon double bond O and nitrogen and hydrogen. These are the groups, okay, that are going to be involved. It means it's the forces between the C double bond O and the NH. Okay, so it's actually between these two. So this will stabilize the protein structure. And for tertiary structure, okay, we have many. To be exact, 4. Okay, so I wrote everything here. For tertiary structure, we have disulfide bridge. Okay, sulfur and sulfur between the R groups. Van der Waals forces between the non-polar and non-polar R groups. Hydrogen bonding if you have polar side chain and the NOF residue. Ionic bond, okay, if we have ionized acid with ionized basic side chain. So you need to choose one. Okay, just choose any one of these. So if I want to choose, let's say I choose hydrogen bonding, okay, then you need to mention properly. So let's say now I put disulfide bridge, okay, disulfide bridge, but they say intermolecular forces, yeah. So I think the disulfide bridge also, even though it's intermolecular forces, maybe I'm not sure whether they are going to be there in the marking key. For example, if you have that confusion, then be just select either this or this if you have doubts. Okay, if you have doubts. So let's say I'm just going to select van der Waals forces. Okay, so I'll just put van der Waals forces. So van der Waals forces, the group involved is going to be the non-polar and non-polar R groups. Okay, this is going to actually create the van der Waals forces of attraction, but there are total 4. Okay, you can choose any. Next, explain the significance of hydrogen bonding in DNA. So this one you see it. For this kind of questions about protein, you can see maximum. Okay, there is going to be 2 marks plus another 2 marks. So please take note. They will not ask too much of question over here, but you need to be able to explain. Okay, so here they say related to hydrogen bonding. Explain about significance in DNA in relation to accurate replication of genetic information. So in accurate replication of genetic information, it is you need to mention there is going to be hydrogen bonding between what? Okay, the hydrogen bonding is between the base pair. Okay, the base pair, okay, they are called complementary base pair. So you can say hydrogen bonding between the complementary base pair. That's going to give you 1 mark. So you need to tell what are the base pair that is going to complement to each other. So A to T, you can just use the A to T, and then C to G. And if you want to mention about the number of hydrogen bonding that will be there also, I have written, but no marks given here. Okay, but if you want to mention, you can mention that there are total 2 hydrogen bondings that can exist for the bonding between A to T. And there are 3 hydrogen bonding that can exist between C and G. Okay, this complementary base pair. So what are the marks? Okay, the marks are given for hydrogen bonding between the base pair. And if you mention A to T and then C to G, then you will get another 1 more mark. So complete 2 marks. Now, many polymers are degradable. Okay, this one I told you to read about it. Okay, because the biodegradable. Okay, whether certain polymers whether they are biodegradable or not, it depends on the structure. Like for example, if you have nylon, nylon is going to be a polyamide. So nylon and polyester. Okay, you can read from the textbook. They mentioned that acid hydrolysis can be used to break the bond. Basically like ester. If you have ester, you can break the bond, okay, between the ester. Like for example, if you have R and R, you can break this particular bond, okay, but you need hydrolysis reaction, okay, acid hydrolysis. So then the polymer can be broken. Another way is by using the sunlight, okay, we call it as photodegradable. So this photodegradable is especially whenever you have polymer that has the carbonyl group, okay, because most of the time the polymer will have this group. And this group, whenever you have C double bond O, whenever there is UV light, okay, this UV light will make that bond between C double bond and O to become weaker, and they are going to break, and this will make them to be biodegradable. So what are the state 2 different process which some polymers can be degraded? One, you just say hydrolysis. No need to be specific because there is also basic hydrolysis. Okay, we have acidic hydrolysis, so hydrolysis will do. The second one is going to be, because it's going to be photodegradable, you can say better way to say photodegradable by using sunlight. So you say by using sunlight or UV light. Now, next is going to be a cyclic peptide B is shown. Okay. Now, for this one, maybe I have written over here. So maybe I'll use a different ink over here so that you can see. So what I did, okay, maybe I think better I'll just do it again. What you can see over here is, okay, you are going to have this molecule. And when I have cyclic peptide B is broken to its monomer by heating under reflux with dilute hydrochloric acid. So the amino acid, okay, and two other products are formed. So you have one of the amino acid here. So I want to know what are the others, okay, but you see, this is going to be breaking the bond, okay. It's a hydrolysis. So the bond that will be broken is going to be the bond between carbon double bond O and an H. This particular bond will be broken. Okay, the peptide bond will be broken. So we need to break. So I'll just put it here. This bond is going to be broken. This bond is going to be broken. So I'll write down first. Sorry. Okay, I've highlighted which are the bond that will be broken. And when that bond is broken, okay, I will write down, okay, what will be the possible structure that you are going to obtain. So for this one, you will get NH, okay, you will get another H. So this one is bonded to another carbon, and then you have another carbon, double bond O. So this part will be OH. Okay, you have this structure. And for this structure, this is NH2. So I put NH2 bonded to carbon, bonded to another carbon, bonded to benzene group, and then bonded, okay, this carbon is also bonded to another carbon, C double bond O, and then this one will be OH. Okay, so I'll just put it as, okay, this one, and then you have this one for this. So here NH, so bonded to carbon, and then this carbon is bonded to carbon, bonded to another carbon, bonded to benzene, and then this carbon is bonded to another carbon, double bond O, and then OH. So this one belongs to this. NH2 bonded to this carbon, then another carbon, double bond O, OH. For this one, so I have C double bond O, OH, then bonded to another C, and this C bonded to NH2, and then this carbon is bonded to another carbon, and that carbon consists of OH and also CH3, another CH3. Okay, you can just put. Okay, two more. So NH2 bonded to this carbon, then you have another carbon, and then you have this, and the carbon here bonded to another carbon, double bond O and H2. going to be for this. Carbon double bond O, OH, then another carbon, NH2, then one carbon, another. Okay, done. Now, if I put it down, they say that, okay, there is going to be threonine, okay, threonine. Now, if you look at threonine, okay, this structure is the same as this structure. Okay, it's the same as this structure. And you are looking for two other groups, okay. So here, when I see the groups, the one that I circle over here, I only see like, if this is one, this is the same as this, and it is the same as this, it's the same as this. And if I give you number 2, this is going to be 2 is the same as this 2. Okay, you can see all of them are the same. Let me check here. COOH, carbon, NH2. Okay, just double check, yeah. So what I will achieve here is I am going to have one structure, okay, that is going to be attached to the benzene. Another structure is without any benzene, which is going to be the structure. Let me check. Yeah, this one is C double bond C, CC, OH, and then CH3. And then this carbon is bonded to COOH and then NH2. So this structure, okay, it's not belong to this. I think this structure belongs to this, is similar to number 2. This is similar to number 2. Okay, so here what I need to write is this C double bond O, OH, C double bond O, OH, C, and then NH2. This is what I need to write. And another one is this one. Okay, so C, C, COOH, NH2. Okay, you can write it like this. Okay, or okay, you want to give it in skeletal formula also can. Okay, but whatever it is, okay, make sure you write properly. Make sure all the carbon are all written properly with all the proper bonds and so on. Okay, you will get this too. Okay, so this one belongs to this one belongs to this. So identify first, and then using the 3-letter abbreviations, okay, given in the data booklet, complete the sequence. Now, this is, okay, threonine. Threonine, they put THR. So I found out, okay, that, okay, this molecule, the one that it has number 1 over here, okay, you can check in your data, you can check in your data booklet. Okay, you will see what you need to see is going to be how to see is, I think here, hold on, yes, C double bond O, and then this is OH. How to see is just look at this portion, this R group. Okay, you will notice that, okay, if the R group is like this, then they will say the abbreviation that we supposed to use is PHE. Okay, for this one, okay, if I have something like only H, okay, if the R group is only H, okay, the R group, this is going to be the structure. If your R group is only H, then they say this is going to be glycine. So you just need to put, okay, because I found out this is going to be 1 1. So 1 1 PHE. And then we found out this is going to be 2, which is similar to this. So this is gly. And then the rest are the same. Okay, PHE, PHE. And then you complete this one. This one you look at your data booklet. Now, name 2 analytical techniques that can be used to separate amino acids. Now, to separate amino acids, okay, you must use electrophoresis. Must, yeah. There is no. If you want to separate amino acids, you cannot ignore electrophoresis. Okay, electrophoresis. And okay, once you separate the amino acid, you can test. You can do further analysis using thin layer chromatography. Another way may be paper chromatography, but other than that, okay, they are not accepting. Yeah, so you can either use thin layer chromatography and electrophoresis, or paper chromatography and electrophoresis. Okay, don't simply give answer mass spectrometry and so on. No. Okay, this one you need to analyze analytical technique. Okay, so you need to separate the amino acids first. Okay, once you separate, okay, how do you separate? Electrophoresis. Then you need to put separate them. Okay, so you need to also use the thin layer chromatography, or you can use paper chromatography. It's fine. Okay, 1 mark. Now, number 7. Number 7, define the term electron affinity. Now, electron affinity is not just ability. Please remember this. It's not ability. Okay, I think students get confused with electronegativity. Electronegativity is ability, okay, of any element to attract the covalently bonded electron to itself. Okay, but electron affinity is different. Electron affinity is not ability. It is the energy change. Okay, it's the energy change when one electron is added to each atom or ion in 1 mole of gases, atom or ions. Okay, so please remember this. This is the definition. 1 electron is added to each atom or ion in 1 mole of gases, atom or ions. Define the term lattice energy. Okay, this is also very popular when you want to define energy change when 1 mole of ionic compound is formed from the gaseous phase or gaseous ions. Okay, that's going to be 2 marks. Okay, so the 2 marks is coming from, okay, it's coming from the energy change, okay, when 1 mole of ionic compound is formed. Okay, so that's going to be 1 mark. Another 1 mark is to tell that it is going to be in gaseous phase ion or gaseous ion. So if anything missing here, okay, you will not get the mark. Now use the following data and relevant data I have calculated for you, okay, to calculate a value of enthalpy change of formation. Now, if you want to calculate the enthalpy change of formation, first thing is to write the formation equation. So I wrote the formation equation. Zinc Br2 solid. So if I want from, it must be formed from zinc. Formation means you form from its standard condition. So zinc is always in solid form. Br2 is in liquid form. So it must be something like this. Then I need to think, or do I have formation data or other data that I can use? In this case, I don't have formation data. So I need to use the longer method, which is going to be the Born-Haber cycle method. So I need to construct the Born-Haber cycle method, and they didn't tell you to construct. Okay, but okay, here you see you need to construct an energy cycle. Okay, so it is some sort of a hint for you already. Okay, but okay, even though it's 4 marks, okay, you need to show them your working. So the working, how do I show? Okay, so I start from here, zinc in solid form and then Br2 in liquid form. I start from here. Now, what I need to do, okay, first I change them into zinc in form of gas. That is going to be enthalpy change of atomization. Okay, so that is going to be 131. I put 131. Then after that, I need to change the Br2 liquid to gas. Okay, so this one is going to be vaporization. So you just put 31. So it changed into gas. Now, next step, okay, is to change, okay, zinc is already in gaseous form, one atom already. But the Br, okay, there is no atomization data. You can see there's no atomization data. Okay, so I still need to change it into Br, atom, 2 atoms of Br. So how do I do that? I go and look at my data booklet, find out the bond energy between Br and Br. And you will find out that in the data booklet, it is written as positive 193. Okay, positive 193. If you want to break the bond between Br and Br, okay, it's there. So you need to look for, okay, the mode. I think the one that you need to look is, let me show you. Yeah, the one that you need to look is the bond between Br and Br, not at the polyatomic. So here you look from, okay, this is polyatomic. Don't look from here. Okay, polyatomic means you have multiple atoms. Okay, so you always look at diatomic molecules because Br is going to be a diatomic molecule. Okay, so Br and Br you look at here 193. Okay, quite simple. Okay, you just look over there. Once you have that, okay, we just continue. Okay, just put the 193 there. Do I need to times by 2? The answer is no, because Br and Br, when you break, you are going to get 2 Br. So it's 193 is enough. Okay, no need to times 2. After that, okay, you need to change into zinc 2 plus. How do I have zinc 2 plus? You need to have first ionization energy and second ionization energy. So this is the data I got from the, I received from the data booklet. So 908, and then the second ionization energy for zinc is going to be 1730. So I put it over there. The next part is the Br will join with the 2 electron to give you the 2 Br minus. This is what we call electron affinity. And electron affinity is going to be negative. So from here, they drop. Okay, so I just put 2 times 325. And the last one is going to be zinc gas and then Br minus gas. This one is what we call as lattice energy. Okay, the energy required to form bonds for them to be in lattice. Okay, for them to form the solid NaBr2. Okay, so the solid zinc bromide, sorry, zinc bromide. So once we have that, okay, I calculate. I will notice when I add these two numbers, I get 3328. When I add these entire numbers, I see 2993. It means that this zinc Br2 solid must be lower a bit, okay, than this line. Okay, why? The distance, you can see the distance. When it is lower, it is just telling me automatically this is going to be a negative value. It's going down. So when it's going down, so we need to calculate this. Quite easy to calculate. 3328 minus 2993. And at the end, because it's going down, you need to give me the value in negative. When I do that, yep. Any question? Okay, when I do that, I will get the negative 335. If you want to show using the clockwise equals to anti-clockwise also can. Okay, please go ahead. Okay, please go ahead. If you're using this method also, make sure, okay, my advice is, if you want the total 4 marks, okay, don't waste any of the marks. So I will strongly suggest to write down 131 plus 31 plus 193 plus 908 plus 1730. All these are clockwise. So plus 2 times negative 325. Okay, plus all these clockwise. So plus negative 2678. This is anti-clockwise equals to enthalpy of formation. So you calculate, you are going to get enthalpy of formation is going to be negative 335. Okay, so if let's say the examiner wants this method of working, so you can also write it down, no problem. Now the lattice energies of these three compounds, they are shown, and they say explain why there is a difference between lattice energies of zinc bromide and zinc chloride. Okay, the difference over here is we know that the zinc chloride is going to be lattice energy is more, okay, compared to zinc bromide. So why zinc chloride has more lattice energy? Okay, the answer is quite simple. The only thing that is changing is not the cation. The only thing that is changing is going to be the anion. And this anion, Cl minus and Br minus, okay, Cl minus, okay, is going to be smaller, okay, Br is going to be bigger. So if you have bigger ion, okay, the bond between, or the bond energy between, ability to form bonds between zinc 2 plus and the Br will be weaker, okay, because they are bigger. Okay, Br is bigger. So here, okay, what is going to, why there is a difference between that? One, your answer, you need to mention about, okay, the size. Okay, so I wrote it over here. Br is going to be a larger ion. So one. And then, okay, the lattice energy, therefore, okay, will be lower, okay, than zinc chloride. Sorry, it's lower than zinc chloride. Okay, therefore we can just say that the attraction, okay, between the zinc 2 plus and Br minus is going to be less. Okay, so you explain about that. It's 1 mark. Explain why there is a difference between these two then. Okay, now this is going to be zinc 2 plus is going to be the same. Okay, but you see here Cl and O. Cl is Cl minus, O is 2 minus. The charge is more. How about the size? When we look at the size for oxygen, okay, in comparison to Cl, oxygen is smaller, okay, smaller ionic radius. So here I will say for zinc oxide, okay, the O2 minus is small and has higher charge. Okay, because they are small and having higher charge, it means the ability to bond, okay, ability to bond with zinc, okay, is more. So if there is going to be more ability, okay, therefore the lattice energy will become bigger. Okay, bigger when, in what sense? Which one will be bigger, zinc chloride or zinc oxide? The one lattice energy is more for zinc oxide. Okay, because one, okay, smaller O2 minus, smaller ion, and at the same time they have more charge. Okay, so ability to bond is more, lattice energy is more, zinc oxide. Please mention about, okay, please mention about this small and higher charge. That will give you another 1 more mark. Okay, now next question, number 8, the last question. Define the term standard cell potential. Now standard cell potential is going to be the potential difference between two half cell or two electrodes in a cell. Okay, so different potential difference between two cells, okay, two half cell under standard condition. If you just say standard condition is not enough, you need to mention that it is going to be at 1 atmospheric pressure, 298 Kelvin, and all the solutions are in 1 mole per dm cube. So you need to mention all this. If not, you will get only 1 mark. Now, an electrochemical cell is going to be set up to measure the standard electrode potential. This is going to be, you go and look at your my PowerPoint and your textbook. These are going to be, both also are aqueous. Okay, the electrode is also aqueous. Okay, the electrolyte is also going to be aqueous. And then you have, this is going to be the gas, okay, gas method, okay, the Cl2, and then you have Cl minus. So complete the table with the substance used to make the electrode. Now for this one, okay, this is going to be for this CO3 plus and CO2 2 plus, the electrode that are suitable for this is going to be platinum. Okay, you want something that can able to conduct electricity better. And then for the Cl2 and Cl minus, okay, always remember if we want to measure the E cell related to anything that is involving gas, it must be using platinum, because they are not they are able to be resistant, okay, to corrosion. Okay, so they are also inert. Okay, they don't react, so we use them. Okay, the only potential downside of this is going to be it's expensive. That's it. Okay, now use the data in the data booklet to calculate the E cell. This is very important. Okay, you have this. Okay, using this, I'll construct the standard reduction potential. So I construct the standard reduction potential, standard reduction potential. This is very important. You look at your periodic, your data booklet, and you look for the number. Okay, I will notice that for this number is 182. 1.82. Okay, 1.82, and for this I'm going to get 1.36. Okay, so next thing that I need to do is to identify which one is more bigger. I notice the first equation is more bigger. It will move to the front, and this one is will move to the left. Okay, because of the 1.36 and 1.82. Now, once you have that, it means if I want to calculate the E cell, it's supposed to be 1.82 plus, okay, this is going to go to the left, so it's going to be negative 1.36. So when I do this calculation, I will get 0.46, and this is going to be plus. Okay, please remember this. So it's going to be 0.46, okay, volt. Write an equation for the overall reaction. Okay, quite simple also. CO3 plus electron, okay, to become CO2 plus. And this one is going to the left. Okay, so it's Cl minus. It's going to give you Cl2 plus two electrons. So I need to eliminate the electron. Okay, so what I need to do, I put 2, I add electron, and electron will be gone. Okay, so I will have 2 CO3 plus. Okay, let me share the screen again. So we only use platinum for metal ion and gases. When do we use metal electrode? Now, for this one, okay, to answer this question, Justin, platinum, okay, we use for uh, the metal and metal ion. Okay, we use, you check over here, metal and metal ion. If I'm not mistaken, we use the metal. I think for the ion and ion, and for ion and gas, we use the platinum. Okay, let me actually share the screen for the electrochemistry part. Okay, this is what we learned last time. Hold on, yeah. Okay, so metal ion, non-metal and non-metal ion, ion and ion. Okay, so if you are using, you see, Justin, this is what I mean over here. If you are using metal and metal ion, okay, so you are using the electrode, we are using the copper, the metal itself, okay, the metal itself. But if we are using the non-metal and non-metal, for example, if we are using gas and gas, okay, hydrogen gas and Cl2, so both also we use platinum. And if you are using ion and ion, for example, Fe3 plus and Fe2 plus, you cannot use iron, okay, as your electrode. It must be platinum. Okay, it must be platinum. So I hope you understand this one. Okay, so so we use platinum for metal and metal ion and gases. The response is no. We only use platinum for metal ion, and non-metal and non-metal, which is gases. Okay, when do we use metal electrode? When it is going to be metal and metal ion. Okay, Justin? Okay, so let me move on. Okay, so here, where did I stop? Okay, so platinum and platinum, yeah, this one is done. Okay, this is done. And okay, this is done. I don't know which one I did until, I think I've done until this. Okay, platinum and platinum. And then when you have this, you learn how to calculate. Okay, and then we want to include all of them. So the 2 electron and 2 electron you cancel. Okay, so I want the electron to be gone. So I will have 2CO3 plus Cl minus. You are going to get 2CO. Sorry, it's going to be cobalt. Cobalt 2 plus Cl2. So this one must be 2. Okay, I think that's it. Okay, this is going to be the equation for the overall reaction. Okay, so if you want to write aqueous, okay, aqueous, and this is going to be gas, go ahead. Yeah. Now, a fuel is an electrochemical cell, okay, that can be used, okay, to generate electrical energy. So you have this methanol oxygen fuel cell, blah blah blah. They have given you this, okay, but I think the question what they want to ask you is to calculate the volume of CO2. This is very important, the beginning part of the calculation. Okay, so here when you want to calculate the volume of CO2, you need to look over here, 6 electron. Okay, if you have 6 electron, it means that 6 Faraday is required to form 1 mole of CO2. You look at this. Okay, we are looking for the CO2. So 6 Faraday is going to be for 1 mole. So first we find the Q equals to IT. Okay, so current is 2.5. Okay, the T must be in second, 30 times 60. Okay, you can calculate also. I'll calculate for you. Okay, so 2.5, 30 times 60. So 4,500 joule. Okay, so when you have this, okay, when you have this is going to be the joules that you have. So 1 Faraday, okay, you need to memorize this, 96500, yeah. So 1 Faraday is going to be 96,500. Okay, you can refer to your data booklet. Okay, so this is, I think it's column, yeah, column. Okay, so this one is going to be how many columns? Okay, it's going to give you 1 mole of CO2. So when I calculate this, 6 times 96500, I'm going to get 579000 column for 1 mole of CO2. I want for 4,500 only. So 1 column, 1 divided by 57900 mole of CO2. So I want 4,500. So 4,500 column is 4,500. You times this. Okay, so 579,000 mole of CO2. Okay, 4,500. You will get 7.772 times 10 negative 3 mole of CO2. I want volume, okay, and I know that 1 mole of CO2, okay, they will occupy 24 dm cube of volume, okay. So just times, okay, I will get how many dm cube, okay, just times 24 times 7.77, so times 24, I will get 0.1865, okay, dm cube. I want in cm cube times 1000. So when you times 1000, 186.5. I think better three significant figures. So we just change it into 187 cm cube. Okay, that's it. Okay, for this paper. Okay, so here, okay, they are asking us about name the functional groups in addition to the benzene ring present in phenolphthalein molecule. So this is going to be phenolphthalein molecule. So in addition to benzene, we need to name certain functional groups, okay? And when we see the groups over here, I do see this one, okay, which is going to be ester, okay? And when I see this, okay, please do not just simply write it as hydroxyl group, because hydroxyl group, okay, is different, okay, because hydroxyl group is just can be referred to alcohol, normal alcohol, or is it actually for the phenol, the benzene attached to alcohol. So it is important, okay, it is important to mention, okay, what kind of functional group is this. Okay, Lavi, you can go now. So here, okay, rather than just simply mentioning them as hydroxyl group, it is better, or I think it is important, okay, you can check in your marking key. They don't actually mention it as hydroxyl group, they mention it as phenol. Okay, so please take note of this. So name the functional groups, okay, please remember these groups, okay, more than one. So even though it's only 1 mark, okay, they are expecting more than one. So one is going to be ester, another one is going to be not hydroxyl group, it must be phenol. Please be very, very careful in this, okay. Now, phenolphthalein reacts separately with two regions shown in the table, okay. Complete the table by drawing the structure of organic products form. Part of the structure has been given for you, stating the types of the reaction. So we need to actually draw the structure of organic compounds form. So now if you have excess hot sodium hydroxide, okay, we need to know that, okay, if you have hot sodium hydroxide, okay, if I try to make it nicer, I will bring it down. Okay, this is going to be the structure of phenolphthalein. So I copy, I put it here so that easier to see. Okay, this is going to be your structure of phenolphthalein. Now, if you look at this structure of phenolphthalein, okay, when you react with excess hot sodium hydroxide, what is going to happen? The first thing that should be coming in your mind is your hydrolysis process, where your ester bond will be broken, because we have two types of hydrolysis: acid hydrolysis and sodium hydroxide hydrolysis. Okay, acid and base hydrolysis. So you are going to actually break the ester. But, okay, there is another important reactions that you need to actually take note, which is going to be the reaction between the phenol, okay, with the sodium hydroxide. Because phenol can react with hot sodium hydroxide, okay, to give you the salt, okay. So here, what will happen is basically you are going to get this, okay, then there is carbon, so double bond O, supposed to be, okay, carboxylic acid, Okay, supposed to be carboxylic acid. Just imagine you have something like this. Okay, R group, another R group. When it is broken, I am going to get RC double bond O, OH, and then ROH. Now, because this is sodium hydroxide, okay, sodium hydroxide, they do react with the excess sodium hydroxide, they do react with the carboxylic acid. So you are going to actually get a further reaction to be RC double bond O, O minus Na plus, and then this H will join with the OH to give you H2O. Okay, this one last time, okay, we already learned. Okay, so here what do I need to write? Okay, I need to write that, okay, there is going to be something like this, and then O minus, and then there is an A plus. Okay, instead of just having the carboxylic acid. And okay, please take note the other part. Okay, the other part, okay, they are going to be O. Okay, and then they are going to be joining with the H over here. Okay, the O join with the H, so you have OH. Now, also don't forget this part. Okay, they will react to give you, okay, to give you O minus and A plus. O minus and A plus. Basically, it's going to be something like a phenol. Phenol, they react with sodium hydroxide to give you sodium phenoxide, they call it, plus H2O. Okay, this one we have already learned. Okay, so they do react, okay, to give you water. Okay, so this is going to be the organic product structure. Okay, in the marking key they have mentioned plus water over here. Actually is correct. Okay, because why? When you do hydrolysis, when this is broken, you are going to get water. But again, please take note, they want organic product. Okay, water is not organic product. Okay, so even though the marking key mentioned, okay, I don't think so we need to write. So what do we write if they ask for observation? Now, if they ask for observation here, okay, because you are heating it, okay, and then you're getting H2O, okay, in this case, I don't think so they will ask for observation, Aneta. Okay, because I think the maximum observation that I can see over here is probably the formation of steam of water, the water vapor. So maybe if the only thing that you can mention over here is going to be white fumes release or water vapor. I don't think so you can say water vapor. So I think fumes will be released or something like that. Or you can say, because sometimes the fume, the steam, when it is released, they will condense, they are going to condense and form water droplets at the top of the beaker or something like that. So if you want to mention that fumes will be released and then at the top, okay, we can see water droplets, droplets of water or something, droplets of liquid. That will be one of the suitable observation. Okay, can Aneta? That's the only thing that you can write. Okay, unless we are talking about HCl, hydrogen chloride gas, then it's white fume of gas. Okay, but in this case, you need to differentiate the white fume of gas with water because I want to mention it's going to be water. So what type of reaction is this? Okay, this is going to be hydrolysis reaction. Okay, it's going to be a hydrolysis reaction. And here we have another reaction when you are using excess Br2. Okay, what will happen? The answer is quite simple. The Br2 will not disturb, okay, the ester bond. So I will draw the ester bond over here again, okay, based on my phenolphthalein. Okay, it will not disturb. Okay, so for the reaction with bromine, why is the type of reaction is electrophilic substitution? Isn't it, okay, isn't it supposed to be mechanism? Okay, hold on. Okay, I'll explain about that. Okay, so here, okay, so here we are going to actually use this reaction. And when we are reacting with excess Br2, okay, the Br2 is going to come, okay, in a sense of, okay, because excess, okay, do take note that this is going to be OH just now, and this is going to be OH. Now, so we are going to be actually, when we want to think about benzene reacting with Br2, then Br2 should not enter the ring, because why? There is no halogen carriers. But do remember, this is phenol. Okay, phenol will increase the electron density. So that will actually make the Br will be able, okay, to actually the electrophile of Br will be able to attach to the benzene. But the position, because this is OH, they are 2, 4, 6 directing. So this is position 2. Okay, position 4 is taken. Okay, 6. You can see position 2, 4 is taken, 6. So you just need to actually put the Br here, Br here, Br here, Br over here. Now, I understand the question that Aneta mentioned about the type of reaction, because the type of reaction, it can be neutralization, okay, hydrolysis, elimination, and so on. But in this case, we are going to actually substitute. Okay, it's a substitution reaction. Okay, but there is no special reaction, like we don't call it as bromination. I don't think so in the textbook and in our syllabus we call this as bromination. No. Okay, so the best answer for this is going to be somehow similar to the mechanism of the reaction. Okay, that's the reason why we use electrophilic. Okay, electrophilic substitution, because there's no other best term to replace that. Like for example, you see for the benzene, if you want to change benzene to become nitrobenzene, okay, then there are options. You know, you have, this is mechanism is electrophilic substitution. Then this is going to be nitration. Okay, so is it going to be should I write type of the reaction is nitration or electrophilic substitution? Both also should be accepted. Okay, both also should be accepted. So here, okay, for Aneta's question, she's asking me, okay, if we write bromination, is it considered? The answer is yes, it will be considered for me. Okay, it will be considered for me, but I am not sure whether it's going to be considered by all the examiner. Okay, so that why I don't have an answer for that. But okay, most of the examiner, they will refer to the marking key. Okay, therefore I will suggest like this. Okay, let's actually make it like something that we always do. Yeah, make it as a practice. Whenever they ask for type of reaction, please think of other terms that can actually you can use. Like for example, here, okay, you know it's electrophilic substitution, and you also know that this is maybe because it's a mechanism, so maybe it's a bromination. So my answer will be, okay, I will suggest you to write, okay, so this one, Aneta, this is my suggestion, yeah. So you write bromination, okay, bromination via electrophilic substitution. This is what I can suggest. Okay, if let's say you are confused, okay, which one to write, but don't always use this. Okay, don't always use this, because it can actually have some negative impact towards your answer, because the examiner might think that you're simply giving all the answers because you're not sure. But in this particular case, I will answer as bromination via electrophilic substitution. And this is what we learned according to the past year paper. Okay, like for example, you see some reactions and you are not, we have been trained to actually learn about mechanism of the reaction, and suddenly you have type of reaction and I don't know. Okay, I'm not sure what type of reaction is this. I know it's bromine. So maybe, or you say substitution of bromine, then you will be thinking, if I just simply give substitution of bromine, I don't mention about electrophilic, will I get deducted? So if you just say substitution of bromine, okay, most likely you get 0. Okay, that's why I'm actually giving you this example. If you say substitution, you must say electrophilic substitution. So therefore, okay, I will say bromination via electrophilic substitution. That will be a best answer in this case. Okay, so even hydrolysis, If you are not sure, okay, so you just say what type of hydrolysis is this. Okay, this is going to be base hydrolysis or alkali hydrolysis. Okay, so a basic hydrolysis. Okay, up to you, but the answer given is hydrolysis, so you can just make it more specific. Okay, this is my suggestion. Okay, now let's continue. Okay, so you have phenolphthalein is an indicator and it is represented by this formula. Okay, and then the Ka value is given. The indicator changes color at pH of something, and then we calculate the ratio. This is going to be a calculation question. Okay, because Ka equals to concentration of H plus In minus divided by HIN. So if I have Ka value, so I just write down 5 times 10 negative 10 equals to H plus In minus HIN. And I want to find out the ratio of this divided by this. So it means that the ratio, okay, the ratio is 5 times 10 negative 10 divided by the concentration of H plus. Okay, so how do I find the concentration of H plus? Then they say, okay, the pH is given. So we know the formula negative log, okay, negative log 10 concentration of H plus is going to be 8.8. That's the formula. Yeah. pH. So if I want the concentration of H plus, so I need to actually find 10 to the power of negative 8.8. Okay, this is quite simple. Yeah, make sure you use your calculator properly. You just need to press shift and then press log. Okay, you will get 10 to the power of something. Make sure, okay, this is very important. Make sure you input negative 8.8. Okay, it's not automatically input for you. Make sure, okay, you will get 1.585 times 10 negative 9. So you want the ratio. If you have the value in the calculator, you just put 5 times 10 negative 10 divide by answer. So you will get the ratio. Okay, you 5 expansion negative 10 divide by answer. I will get the answer as 0.315, and that's going to be my answer. Okay, please write down all this. Yeah. Now, methyl orange is another acid-base indicator. Okay, the structure at this pH, okay, is shown. Okay, at pH 4.4. Okay, on the structure of methyl orange, circle the bond or bonds that make this compound a dye. Now, if it is a dye, okay, we have already learned diazotization reaction. Okay, the bond that will be responsible to give the color will be this one. Okay, this is going to be the bond that you're supposed to circle. Now, the color of this indicator changes from pH 3.2 to pH 4.4. It means that, okay, it means that this is going to be having a lot of H plus. Okay, having a lot of H plus. So suggest, okay, the structure of methyl orange at 3.0. Assume the structure is unreactive. Okay, which one is unreactive? It means this one will not react. Okay, will not react. So now, if I want to actually look at or suggest, okay, a structure, it means there should be a change that will happen to the structure of methyl orange. And what is the change? The only reasonable change is to think about in this way. If I have a lot of H plus at that pH, that H plus must be able to react with my methyl orange. So I need to think about what part in my methyl orange will react. So if I think in that way, I know I cannot touch this part. The only thing that I can touch over here is something that has lone pair. Okay, because H plus, it requires electron. I have lone pair here. I have lone pair here. I have lone pair here. So I can actually choose any of the nitrogen over here. There are 3 nitrogens over here. So if I want to actually suggest, okay, I will suggest like this. Okay, so let me actually draw this again. Okay, if I draw this again, what I will suggest is going to be, I will suggest maybe I just take this nitrogen, for example. I take this nitrogen. Okay, so this nitrogen will join with the H plus. So I will just say, okay, after joining with the H plus, okay, they will join. Okay, what happens now? I am losing electron. One lone pair. It's like I'm losing electrons over here. So when I lose electrons over here, okay, when I'm sharing, or like in this case, if you are thinking about like I am joining with H plus, okay, you are not joining with something that is going to be neutral. So the charge of that H plus will come over here in this molecule. That's the reason why the charge positive will come over here. Okay, because it will take that charge. Like similar, like I give you one example, ammonia. Okay, when they want to actually form the bond with H plus, okay, when they form the dative bonding, okay, they are going to form NH3. So H3. So this one will be joined with the H plus. Okay, so I need to make sure that the entire molecule is plus. Okay, that actually represents what has been happening over here, why there is plus over there. Okay, so please take note. So of course I can actually write it in this way, or okay, you can also write it here, also can, or you can also write it here, put the H here, and then this will become plus. Okay, there are three answers that you can write. Okay, so that is going to be the structure. Now methyl orange can be synthesized as shown. Okay, so if I synthesize this, okay, you have few steps. Okay, step 1, step 2, okay, and then you get the methyl orange. Okay, so now I need to actually think. Okay, when I want to synthesize methyl orange, okay, basically this is going to be structure of a dye. Okay, so you need to relate to your diazotization reaction. So whenever you want to form that dye, any form of dyes, okay, we have to change the nitro group, okay, the N2O, okay, you need to change it into amine, okay, or phenylamine. Okay, so the first step, okay, that I will suggest is to change it into amine. So I will draw. So SO3 minus Na plus. So this one you change it into NH2. Okay, once you have that, okay, we need to actually change the amine, okay, into something that is able to form the diazotization over here. So it means there is another step, okay, which is going to be you are going to react, okay, with this NaNO2, okay, plus ACl, concentrated ACl. I hope you remember this. You are going to form this benzene diazonium salt. Yeah, so this one is going to be, okay, in a simple way. Okay, I will actually write it down in this way. So SO3 minus Na plus, nothing. Okay, so here you need to actually mention, you see here, this part is coming from here. Okay, so here you must have N2, sorry, you must have N2 plus. Okay, you can write it in this way, or if you want to write it in full form also can, N double bond N, then you want to write plus also can, or you want to join with the Cl also can. Okay, up to you. Okay, but I will normally write it down as N2 plus, easier for me to see. Okay, so once I have that, okay, then you are going to have this what we call as coupling reaction. Okay, coupling reaction, and you are going to have this reaction. Yeah, so here you are going to get this methyl orange. Okay, deduce the identity and draw the structures in the boxes. Okay, already. Okay, this is going to be phenylamine. Okay, this is going to be benzene diazonium salt. Okay, so suggest the region and the condition. Okay, the region that we need to do, okay, to use. Okay, this one is reduction of nitrobenzene. So you need to use SN, tin, and concentrated HCl, and then I think you need to heat. Okay, you need to heat. So I'll just put SN, concentrated HCl, heat. Step 2, okay, very important as well. Okay, you need to make sure, hold on, yeah. Step 2, you need to make sure that, okay, you include, okay, the NaNO2, okay, with the HCl. Okay, so after that, please make sure, okay, to tell that this happens. I think you need to keep it less than 10 degrees Celsius. Okay, so I think I'll just put less than 10 degrees Celsius, because why? If you don't do that, okay, this salt, okay, they will decompose to give you nitrogen gas. Okay, so we don't want that. So you need to write down NaNO2 and then HCl. Okay, I think it's concentrated HCl. Okay, concentrated HCl, and then temperature. I think some books they say 0 to 10. Okay, or you say less than 10 or 10, up to you. Yeah, please actually include that. Now next, okay, define the term partition coefficient. Okay, so what is partition coefficient? Okay, partition coefficient is going to be the ratio. Basically, it's a ratio of the concentration. Okay, ratio of concentration of what? Concentration of solute. Okay, of solute into immiscible. Okay, they are not going to mix well. So two immiscible solution, but make sure, okay, you need to actually explain in equilibrium. If you don't mention in equilibrium, okay, then it's wrong. Okay, you will not get that 2 marks. Okay, so ratio of concentration of solute in two immiscible solution in equilibrium. Now KPC, okay, for benzoic acid between octane 1-ol and water is given 79.4. A solution, okay, they are given, let's say you have 0.4 gram of benzoic acid. That's a solute. Okay, this solute, they are going to be mixed, okay, with the octane 1-ol and also water. Okay, and then we want to calculate the mass of benzoic acid extracted into water layer. Now this one I want you to be very careful, because I think there is a shortcut. Maybe some students, they do the long cut and eventually spending a lot of time. Now for this question, you do not need to change it into number of moles. Okay, you can actually use directly gram per the concentration in form of gram per cm cube or gram per dm cube. Okay, it's okay. Okay, why? Because in the end, okay, it's still going to be concentration. Okay, so please take note, concentration can be measured using mass over volume, okay, or number of moles over volume is still the same. Okay, you do not need to actually change it into mole, then after that you calculate, then after that you change into you get the answer in gram, then after that you change into mole, and no, you get an answer in mole, then change into gram. You do not need to do that. If you do that, then it's going to be the same working, but you are going to actually do extra work only. Okay, so what I will suggest straight away, use, okay, here, okay, they say benzoic acid in octane 1-ol and water. So it means that the one that is on top, this one I told you already, whenever they mention in the question, so it means that the ratio, it must be the solute in octane 1-ol divided by the solute in water. Okay, just remember this. No need to crack your head on which one comes first. Okay, no need to worry about that. So 79.4 equals to concentration. So in this case, concentration, I'm using the mass straight away. Yeah? Now, the mass, okay, I have 0.4, and obviously some of the mass will go into water. So imagine I'm taking it as X, the one that will go to the water. So I put 0.4, the one will go to water, I put X. What is the concentration now in the octane 1-ol divided by 25? Okay, take note, I don't even change the 25 cm cube into dm cube, no need. Okay, it will, as long you're using the same unit up and down, it's still okay. Okay, so here divided by, okay, this is octane 1-ol, concentration in water. Okay, the one that dissolve, okay, just take it as X. Okay, divided by, okay, the water is 125, okay, divided by 125 bracket. And then you just need to find what is going to be X. Okay, that's the mass of benzoic acid extracted into the water layer. So you just need to find X. So I think quite easy. You just times by X. So here 79.4 X over 125 equals to 0.4 minus X divided by 25. I times by 125, I get 79.4 X. 0.4 minus X, 125. So this one is going to be 5. Okay, when I times, this is going to be 2 minus 5X, 79.4X. When I bring over there, it's plus 5. Okay, 79.4 plus 5. I am going to get 84.4X equals to 2. Okay, so I just need to divide. So X is going to be 2 divided by 84.4. And hold on, yeah. 2 divided by 84.4. Okay, my answer X is 0.0237. Okay, let me check the marking key. Yeah, it's correct. Okay, for this type of question, water is always denominator. No, Gabriela Nicole, it doesn't work that way. Okay, in this case, for this kind of question, it depends on how they put the KPC. When they say the KPC, okay, of benzoic acid between octane 1-ol and water, it means octane 1-ol comes first, then water. So this one comes on top, this one comes below. So if let's say they say KPC between water and octane 1-ol, then it's going to be the other way around. Okay, please take note of that. Or maybe in some questions, they will require you to think about it. Okay, like this is 79.4. Okay, so this one is going to be, I think rather than thinking, I think they will just ask you to, because sometimes you need to think, like if you have the more value, okay, 79.4, okay, compared to having it in decimals, it means that the benzoic acid dissolve more in octane 1-ol compared to water. Okay, so that is our thinking. Yeah, so benzoic acid dissolve more in octane 1-ol compared to water according to the question. Okay, if I have 0.79.4, then it's going to be the other way around then. Okay, so please take note of that. Okay, anyway, for this one, okay, it's going to be, this is the answer. Now you see KPC, this is actually what I told you to look. Okay, KPC between octane 1-ol and water, okay, is different, okay, compared to benzoic acid. Now this is going to be a ketone, you can see. Okay, this is going to be R, okay, C double bond O, another R. Okay, it's a ketone. Now ketone, I just want to ask you, Victoria, is it polar or non-polar?
Polar.
Ketone, is it actually polar or non-polar? I think, yeah, you can actually take it in a, how to say, most of the time, okay, it's going to be depends on what you have over here. Okay, depends on what you have over here. In this case, okay, the ketone, okay, when we look at C6H5, they are going to be, if I compare this with benzoic acid, okay, if I compare this with benzoic acid, I think both of them, okay, ketone or benzoic acid, they are polar. Okay, but if I look into detail, which one is less polar? Okay, which one is less polar? You should be able to identify that ketone in this case is going to be less polar. Why? Because it's going to be the R group is going to cancel with each other. They are going to be non-polar. Okay, so if they are non-polar, okay, we are going to do remember, okay, non-polar, they will dissolve more in non-polar solvents, and polar solvents, they will dissolve more, polar, they will dissolve more in polar solvents. Okay, so this one we have learned earlier. So now, okay, we know that, okay, we are going to actually the reaction is going to be, we are trying to mix them with octan 1-ol. Okay, I know that water is polar. Okay, water is polar. Octan 1-ol is 8 carbon alcohol. Now 8 carbon alcohol, okay, alcohol generally they are polar, okay, but 8 carbon, the number of carbon increases, okay, when the number of carbon increases, that the substance, they become less polar. Okay, they are going to become less polar. Why? Because the increase in the number of carbon, they are going to make it like a aliphatic structure. We call it aliphatic because why? It's a long carbon chain. If you have more long carbon chain, they are going to become non-polar. So here, this is going to be considered to be non-polar. And if you compare here, non-polar and the benzophenone is non-polar, okay, it means that, okay, your benzophenone will actually dissolve more in octan 1-ol compared to water. It means that, okay, if you dissolve more, earlier it was 79.4, now your KPC will be expected, okay, will be expected to be higher. Okay, will be expected to be higher. Okay, they didn't ask, okay, but I just going to mention over here. KPC will be expected to be higher. Why? Because the benzophenone is non-polar compared to benzoic acid and will dissolve better in octan 1-ol. Okay, that's going to be the answer. Okay, it will dissolve better in octan 1-ol. That's why the KPC is better. Higher. Yeah. Now next, okay, hold on, yeah. Okay, benzophenone can be synthesized from benzoic acid in 2 steps as shown. Okay, so in step 1, a compound J, a reactive intermediate is formed. Okay, so compound J is reacting with the organic compound to form benzophenone. Now, when they say reactive, okay, you see this is going to be carboxylic acid. Carboxylic acid is always unreactive, so you need to change it into something that is reactive. In chemistry, we learn, okay, if you want to have any reactions, okay, better change them into acyl chloride. Okay, so the J must be in this form. Okay, change it into acyl chloride. How do we change it? Okay, you have 3 ways. Okay, you can react with PCl5, react with PCl3, or react with SOCl2. Each of them, they have their own conditions. Okay, if you have, I think the only thing that requires heat is PCl3. Okay, PCl3 will require heat. The rest are room temperature. Okay, I have written over there. Now, also what you need to notice is the reaction of carboxylic acid, okay, with this PCl5, they will give you POCl3 and ACl, white fumes of gas will be released. And the reaction with PCl3, they are going to give you the acidic H3PO3. And the reaction with SOCl2, okay, they are going to give you SO2, which is going to be a colorless gas, and also HCl, a white fume, okay, of gas. Okay, so one of the way to test for white, I think for alcohol and so on, is by testing it with SOCl2. Okay, please take note the reaction. Okay, these 3 things, okay, they can react with bromo. They can react with the acyl chloride. They can also react with halogen alkene, because we have learned about this in halogen alkene. Okay, please take note of that. Okay, now, so next, okay, is going to be the reactive intermediate. Okay, it needs to form benzophenone. So how do I get suddenly a benzophenone over here? You can see that, okay, there is Cl here, there is no Cl. So the only way is by adding the benzene. It means you are putting the benzene here. Okay, the benzene, okay, they will benzene have each of them has H. This H will join with the Cl over here. Okay, that HCl is going to be eliminated. So you are going to have this structure. Okay, so if they ask you what is going to be the side product that is going to be produced, the side product is going to be HCl. Okay, white fumes also. Okay, and this reaction, please take note, this is going to be AlCl3. It's a halogen carrier. It is also another indicator for us to say that, oh, this is going to be electrophilic substitution is going to happen. Okay, so I must have another benzene, and then they are going to attach over there. And please take note also, okay, this is going to be, yeah, I think this one in this case, okay, doesn't matter because it's just benzene. The position doesn't matter. Okay, but you need to make sure that if they ask you the mechanism of the reaction, this is going to be electrophilic substitution. So the electrophile over here, okay, is going to be this one. Is going to be the electrophile. Okay, please take note. Okay, the electrophile is going to be that. Okay, that is going to be your electrophile, or to be exact, what is going to be the electrophile? Okay, this one. I'll just draw. This is going to be your electrophile. Okay, that is going to be your plus. O, this is plus. Okay, that's going to be your electrophile, and they are going to be attacking the benzene. Okay, now, so deduce identity done, suggest regions and condition for step 1. Okay, this is going to be, you can select any of those three that I mentioned over here. Okay, so if I select PCl5, okay, then it will be room temperature. But let's say I want to actually select something else. Okay, maybe I say PCl3 heat. Okay, then that will be another answer. Okay, please take note. Now, next is going to be benzophenone. Okay, can be also synthesized in 2 steps from bromomethylbenzene. Okay, so this is bromomethylbenzene. And then I can see there are going to be 2 steps over here. This step, okay, of course, KMnO4 heat, this is going to be oxidation reaction. But whenever I look at oxidation reaction, or this one, I look like ketone. Okay, the first thing that will play in my mind is, oh, this is going to be a secondary alcohol, maybe only, yeah. Okay, but okay, when I see the L, there is no OH. Okay, it means that this is not secondary alcohol. Okay, that is going to be not included. So here, okay, what is going to happen? When I see C13 and I have C7 here, okay, so of course there is going to be reaction with another benzene. Okay, something to do with another benzene. Okay, so what is going to be the step? Okay, so basically you are going to have a bromomethylbenzene. Okay, is going to react, okay, with a benzene. Okay, that is going to be the only thing that I can think of. Okay, a benzene. Okay, a benzene, and then they are going to have this. Okay, they are going to react together. Okay, there is carbon here, and then there was Br. Okay, there was H here. Okay, what happens? That HBr will come out. So this thing is going to join together, okay, to give you C and C. And then in a skeletal formula, no need to write the C, so they just put it as like this. Now, do take note, there is no halogen carriers here. So most probably here, if they ask, then you need to have an halogen carrier. Okay, you need to have an halogen carrier over there. And what else? I think that's all. Okay, I think that's all. It will give you HBr. Okay, and then here the oxidation is a bit funny also. Okay, because we learn, okay, when you have CH3, okay, when I oxidize, then I'm going to actually get carboxylic acid. Okay, that is what we have learned. But now in this case, okay, when I oxidize this is automatically going to change into ketone. Okay, so this one, no need to worry about it. Okay, no need to worry about it. Okay, this one, they are not even asking more about it. Okay, so but this is the only logical answer that you can come up for this L. Okay, so I deduce the identity and then draw, done. Name the mechanism in step 3. So this one mechanism, yeah. So in mechanism, electrophilic substitution. The region and condition, so you need AlCl3. Okay, that is very, very important, AlCl3. And then you need benzene because I'm introducing benzene. Okay, and then just heat it up. Okay, heat. So these are going to be the conditions. They didn't ask much about this, so just ignore. Yeah. Now, deduce the type of reaction in step 4. Yeah, of course, oxidation. Okay. So this is oxidation. Deduce the number of peaks that will be present in carbon-13 NMR spectrum of benzophenone. Okay, so you see, this is very important. Carbon, okay, carbon environment. This is carbon number 1. So this is going to be also same, carbon number 1. This carbon environment is the same as this carbon environment, okay, symmetrical. This carbon environment is the same as this carbon environment, also symmetrical. This is 3, you can see, the same also. And then this is going to be 4, the same as this. And 5 over here. So there are total 5 carbon number of peaks over there. And then identify 2 different environments of carbon atoms that will result in different chemical shift ranges for carbon-13 NMR. Now for carbon-13 NMR, okay, please take note. Okay, there is we need to actually look into benzophenone. Yeah, so you can see. Okay, I know that. Okay, maybe the carbon I can talk about. Okay, the carbon that is actually attached to this like benzene. Okay, normal benzene. This environment. I can also talk about this environment also. Okay, I can also talk about this environment, but I think the one easier is this one because it's a carbonyl group. Okay, it's a ketone group. Okay, so maybe I'm expecting these two. Okay, I'm expecting these two. So if I want to actually write down the environment of carbon atom, okay, one maybe I can say that the benzene, okay, the carbon or the arene or the carbon in benzene. Okay, and I can also mention another one is going to be the carbonyl environment. Okay, if you want, okay, write down the CH, okay, in benzene. Okay, the carbonyl environment, C double bond O. Okay, that is the environment. What is the chemical shift? Okay, here I found out. Later I'll show you 110 to 160, 190 to 220. Okay, you can see benzene and carbonyl. Okay, so if you look at your periodic your data booklet, okay, you will get this. Okay, so I want to look for benzene. So you can see the benzene is around here. Okay, so I'm looking for 110 to 160. And I'm also looking for carbonyl. Okay, so the carbonyl, just look at the next to carbonyl group. Okay, so this the carbonyl group here. Okay, so this one 190 to 220. So this one is different. Yeah, this is the normal carbon next to carbonyl. Okay, so this one is directly to the carbonyl group, the carbon that we want to find out. Okay, this carbon. Okay, if you are referring to this carbon, then we are looking into this. Okay, so that's why I have written it over there. Okay, I've written it over there. Now it's already 10:05. Okay, now I will stop